Alright, so we talked about this thing called DNA. We talked about the importance of DNA, and we got an overall picture of why it's so important and how the discovery of DNA happened. And then we began to talk about the structure. So, what I want you to imagine for a minute is just think of this DNA as a strand. And that's what I'm drawing here. And this DNA strand is made up of bases, and these bases we've talked about. The bases are called A, T, G, and C, and if we're talking about RNA, we need to throw U into the mix, not T. Alright, so with DNA, I want you to then think about, well, off of this strand, we get these bases. And these bases could be an adenine here, and an adenine here, and maybe a thymine there, maybe a guanine here, another thymine that's here, another guanine that's there, and maybe a cytosine that's here. Okay, so this is how I want you to start picturing this DNA molecule. So these bases are basically pointed and exposed in a way onto this long backbone. And this backbone is beginning to make the polymer, and this polymer is what we refer to as the DNA molecule itself. These things are so long that we said they're macromolecules, and I can see them with the naked human eye. So I don't need a magnifying glass or anything to see these DNA strands. They are that long, billions of base pairs long, actually, that begin to hook up. So billions of these bases are inside of DNA. Okay, we talked about this concept that A and T and G and C come to us in pairs. And I told you that we would talk about that in a minute. And this is where we're going to discuss that concept, because what we realize here is that for stability purposes, we want to make these molecules as stable as we can. Mother Nature at least wants to do that. So she took uracil and methylated it to make thymine, because she knew that if the methyl group was there, it prevents many of the enzymes from reacting with the thymine, and this helps increase the stability of the DNA molecule. Something else that increases the stability is that she takes two strands of this polymer unit and she hooks them up together. And I'm going to draw a strand on the top, and I'm going to draw a strand on the bottom. And this is where the pairing comes into the picture, because what happens here is that we line things up perfectly. And what happens is that if there was an A on this strand, well, that perfectly matches up with a T, and we get this nice little marriage that happens between the A and the T base. So here's another A, so that would be a T. Here's a T, so an A would be found on that strand. Here's a G, so G's and C's go together, so there's the C. Here's the T group, so again A and T go together. Here's the G group again, so that would be another cytosine. And then here's a C, so that will be guanine on that ring. So we see two strands. So I'm going to label this as strand 1, and I'm going to label this one down here at the bottom as strand 2. And these strands are what we call complementary. So complementary strands. So complementary strands basically means that Mother Nature kind of makes a duplicate copy, but it's not an exact copy. If it was an exact copy, then that means A would pair up with A, T would pair up with T, and G would pair up with G, and C would pair up with C. It's not an exact copy, it's a complementary copy, meaning, well, these two things come together. Why do they come together in the way that they do, and why do they pair up the way that they pair up? And this whole story involves hydrogen bonding. It's all about the hydrogen bonds, people. So what we realize, or what we will find out, is that a GC pairing maximizes the number of hydrogen bonds between those two bases, right? Bases, hydrogen acceptors. And there's groups, H attached to an N, an O, or an F. That's the definition of a hydrogen bond. You learned that in general chemistry, right? An H attached to an N, an O, or an F. If there's an H attached to an N, O, or F, and it can be attracted to another N, O, or F, we see a hydrogen bond being formed. The GC pairing maximizes the possibilities of hydrogen bonds. Hydrogen bonds are glue that holds these molecules together. We went through a whole lecture on intramolecular forces in General Chemistry 2, and we talked about these hydrogen bonds and intramolecular and intermolecular forces that happen between molecules that keep them together, and forces that I have to overcome to get things to melt and to get things to boil. The same thing happens here. So DNA maximizes the number of hydrogen bonds between the base pairs, and it maximizes the glue that holds the strands together, and then it maximizes the strength in doing so. So DNA begins to become very hard to rip apart. And again, that's good news. I'm looking for stability here. And this is one of the ways that this molecule becomes stable. So if I take a look at the PowerPoint, you're going to see them basically draw out these nitrogen base pairs. And you're going to see this example of the GCs and the ATs coming together and forming the hydrogen bonds between the base pairs. And this is another reason that a purine is coming along with a pyrimidine. So purine and pyrimidine, they're kind of like opposites, male and female. They're coming together to make the match, and they're coming together in that reason because the GC base pair forms 3 hydrogen bonds between the pairing. And then the AT base pair form 2 hydrogen bonds through the pairing. Notice it's this NH2 group, H attached to an N, O, or F, that's attracted to another N, O, or F. The same thing's happening here. H attached to an N, O, or F, and that's attracted to another N, O, or F. That dotted line represents hydrogen bond. Glue, that's keeping the strands glued together, that's keeping stability onto the DNA molecule. That's what it's about. The same thing's happening here. I see H attached to an N, O, or F, dotted line to another N, O, or F. Same thing here. H attached to an N, O, or F, attracted to another N, O, or F, and the same thing down here at the bottom. H attracted or H attached to an N, O, or F, attracted to another N, O, or F. So hydrogen bonds definition, General Chemistry 2 material, all coming back. It's all haunting you now. That is called intramolecular forces, a part of intramolecular forces. Okay, so off of these base pairs, notice in this structure we see a line that shoots off and it says sugar, and then over here a line that shoots off and it says sugar. So we've got to talk about what these sugars are, because we said that was one of the components. We said that one of the components of these whole things are these sugar backbones, these 5-membered sugars that had an aldehyde group on them. So we need to talk about what that means. There is a rule that we use to describe this pairing, and those are called Chargaff's rules. And Chargaff basically says, for every A there is a T, for every G there is a C. And sometimes in undergraduate, for every A there is an F, especially if they want to grade on the bell curve. That's something that you don't want to experience. I did. That's something that you don't want to experience, though. Oh gosh, it'd be horrible. Okay, so for every A there's a T, for every G there's a C. That's Chargaff rule, and that's all that is. It determines that the number of adenines equals the number of thymines. Guanines equal the number of cytosines. If you know the number of one, you know the number of the other. So they should perfectly match that way. So base pairing rules, A goes with T, G goes with C, every single time. Okay, so I'm stopping the video here. Next video, we'll keep trucking on. We'll keep kind of expanding this idea of the structure of DNA and what it's doing and what it will do for us. And our next piece of the puzzle will be the sugars. What kind of sugar are we talking about? What does the sugar look like? What's going to go on as far as the sugar is concerned? But this is the story with the base pairs finally. Okay, so if you flip through the PowerPoint, you'll see some more diagrams, just different diagrams of the pairings that happen and different representations of the H's. The composition of the ATs and the GCs vary. You know, this is one of the reasons that makes us different than a banana. Right? It's the whole ratio and proportion concept. So if you look at our DNA, banana DNA and human DNA are all made up of A's and T's and G's and C's. The problem, though, or the difference that happens, not really a problem, I don't want to look like a banana. So the difference that happens here are the percent compositions. What we will find out is that 25 to 75% GC pairs in bacteria, 39 to 46% of GC pairs in mammals. So if you begin to look at a composition ratio this way, you will actually start to see that the DNA composition is different depending on species and versus other species. So some species have more GC pairs than others, some have more AT pairs than others, but this is one of the ways that a banana doesn't talk, and a banana doesn't grow hair, and a banana doesn't teach chemistry on YouTube. Okay? So with that said, we'll take a stop here. We'll continue on. And again, if you've got nothing else to do, I know it's probably a warm April day, and you probably want to go out to the beach 5 minutes down the road. But you know what? You can't, because you got to sit here and you got to suffer through the DNA lecture module until you get it done, because you probably waited to the last minute and the test is coming around in 2 days. So now you got to cram. See, you shouldn't have wasted all of that time. You could have been to the beach with me today.